Okay, so the next part of the question wants us to find the expectation value of x. Now this is just basically solving a really big integral problem. From the formula, what you should find is that the expectation value of x is just equal to x times the norm of it integrated across the entire space. And what we've done is you've just found what psi of x and t is. Then you just do x times that value and integrate. So let's just do that right now. So let's do this integral first. Notice that because we have the addition signs, we can just split up the integral and deal with them individually. Now notice that if we happen to integrate 0 to a of 1 over a sine squared times some constant of x, then what we're going to find is that we can use the sum angle formula to break this down into two terms. So this is just a trigonometric identity, and what you find is that's equal to... So we can use that to simplify our formula here. Now notice that we've restricted our parameters from minus infinity, plus infinity to 0 to a, because when we have our infinite square well, all the values outside of these points are just going to be 0. So the only value we're concerned about is inside this infinite square well, which goes from 0 to a. So therefore, minus infinity plus infinity goes from 0 to a. And we can continue working through these calculations. Doing this, we're actually going to have to use integration by parts. And the trick to doing that is you write a differential column and a integrating column. And you want to choose a function that will differentiate to go to 0 and will integrate to whatever you want. So we're going to obviously choose x to be our differential and I to be our integral. And what you're going to do is you're going to differentiate x and you're going to integrate 1 minus cos x. So this is going to be 1 and derivative of 1 is going to be 0. The integral of 1 minus cos x is going to be... Well, actually, no, let's break this down. Let's break this down into the two separate integrals. So we can take this to be just cos x then. So what we're going to do is we're going to do 1 over a half x minus 1 over a. So this is what we're trying to do now. And therefore we have our x to be the differential and the integral is cos 2cx. Now to do the integration by parts, you multiply down from the derivative to the integral. And this is going to be 0 times whatever this is, so it doesn't really matter. Now you start off with a plus, minus, plus, and you keep rotating. So writing that out, we can just add those terms up and we're going to get our integral by parts. And what you're going to find is that when you evaluate this, you get 1 over 2a times 1 over 2 times a squared, because the 0 will just cancel out, minus 1 over 2a. So what we want to do is, I think, replace the c's back for what our actual functions were. Yeah, so then evaluating this out, we get the a's cancel, we get a over 4. And I believe this term goes to 0 because sine of 0 is just 0. And then cos a is 0, and cos 0 is also 0. So then this term becomes I think 1 over 4 minus 1 over 4, which is just 0. Yeah, so this term cancels out. So then you end up with a over 4. So yeah, that was a lot of work, and that was just the sine squared pi over ax term. What you'll find is when you do the same thing for the 2 pi over a term, you're going to get a over 4 again. And then you can just use an integral calculator for the last term. But what you should find for that term is to be equal to minus 16 a over 9 pi cos 3 omega t. This will be equal to the integral of the second term, and this will be equal to the integral of the third term. And then you can just collect all those terms up and write them in terms of the expectation value of x. So this term is going to come from the sine squared pi over ax. This term is coming from the sine squared 2 pi for ax. And this term is coming from the cross. And you're going to add those terms up, and what you're going to find is that a over 2 yeah, so for this question I did go a lot more into detail than the solutions the book has. And that's just because I think you need to know where each of those terms come from. So this term is constant, but this term is oscillating in time. And when they ask for the amplitude, they want to know how much that oscillation is going to be. So the amplitude of that is just this value. Now, to get the oscillation frequency, you just take the term that's going to get multiplied by t. So the frequency is just 3 omega. But we know from the question that omega is equal to pi squared h bar over 2ma squared. And those are the values of the amplitude and oscillation frequency.